So this is our last talk for today. Ivan Vergiliev is going to be our speaker. He's a tech lead at Heap. I guess he will say a few more words about himself in his talk, but I want to say a few more words about him because this is the guy that got me into programming, and it's thanks to him that we actually managed to do something like hackconf. So please, a very, very big round of applause for Ivan.
Thanks, Rolo. Hey everyone, my name is Ivan. Ivan, whatever. We're gonna be talking about horizontal scaling, distributed databases, things like this for closing today's hackconf first day. So talk plan, first we're gonna go through an introduction of what the problem is that we're gonna be covering. Then we're gonna go through some fundamental concepts in scaling a data system, and why these concepts are useful. And then we're also going to go through what kind of trade-offs they incur, and like what kinds of things we need to think about when we introduce those things into our system. And then depending on how time goes, some extra credits, which we'll see what it is and what it isn't. Cool. Yeah, about me, I'm currently a tech lead at a company called Heap. It's a startup based in San Francisco. One of the fun things is that beyond working with distributed systems, we also work with a distributed team. So I work in a team with 6 people. None of them is no 2 of them are at a single location. So I work with a person from Lithuania, Italy, San Francisco, New York, and a city somewhere close to San Francisco, but not there. So this is also pretty fun. It has some of the benefits and drawbacks of an actual distributed system, some of the similar failure modes and benefits. Before that, I was a tech lead and founding member of Nippon's Sofia office. And before that, I've been at Google and Facebook for a few internships, SoundCloud when they had a Bulgarian office. And then I also, like from a while back, I have a bronze medal from the International Olympiad in Informatics. Cool, so let's get started. What's the problem that we're going to be discussing? We have lots of data, and we want to store that somehow in a way that allows us to do useful operations. Usually somewhat abstractly defined because we're going to be covering fundamental concepts that apply to like all kinds of different systems. But in short, we're going to focus on cases where the data set is changing or dynamic, as in there are reads, but there are also writes to the data. If the data set is static, like we have a big data set and we want to analyze it, for example, that's a different kind of discussion. Some of the same ideas apply, but usually apply in a slightly different manner. Okay. So we've been doing a bunch of talks on distributed systems lately, and I also started with a disclaimer. Distributed systems are hard. Like there are a ton of failure modes, a ton of things that you need to think about, a ton of systems that you need to administer and all that. And the other thing is that, like, in addition to distributed systems being hard, single system machines, like single instances, individual instances, are super powerful. So you probably don't need a distributed system. So just to give an example for this claim that individual machines are super powerful, Amazon maybe last year launched a new instance type, like a new type of instances called the U6, 9, and 12 DB1. The .metal part means that whatever. .metal part means that there's like almost no virtualization, so like you use almost directly the hardware bit underneath. And the thing that you see in the second field, the 6 terabytes, 9 terabytes, and 12 terabytes, I just want to underline that this is memory. Like this is RAM. Like random access memory. This is not a hard drive. This is not an SSD. So you can go to Amazon, click a few buttons, give them your credit card. Like that's going to be an important part of that exercise. But with a few buttons and like some money, you can get a machine that has 12 terabytes of memory and 448 CPU cores. So you can do a lot with that. And if you can, you probably should. But then, okay, so that's a disclaimer. Now, if you actually do need to scale out, let's see what this is about. So we're gonna cover like 2 fundamental concepts, and then we're gonna go to drawbacks. The first thing that we're going to need to think about is that, okay, we have a lot of data and we have a lot of machines. So how do we benefit from like all these machines? Let's say I'm going to be giving an example with a big table called events that has 1 billion events in it, with an ID, a user ID, and a country for each, where each event happened. So let's say this table has like 1 billion rows. This is probably too small to scale out, but it's like easier to talk about because like after that numbers get more complicated. But like the first thing that we need to do is that we need to split it somehow in order to benefit from all the machines. And like a traditional way to split it is to say, okay, I'm gonna take the first 100 million rows and put them in separate subtable, take the next 1 million rows and put them in separate second subtable, and then so on until we split all the 1 billion events into separate subtables. The subtables are usually called charts or tablets, depending on the system and who's doing the talking. And also this is called horizontal partitioning. And there's like another type of partitioning that's called vertical partitioning. We're not going to be covering that here, but it's also useful in some situations. Okay, so we split the data. Then what we do, we take like 10 worker machines and put each table, like each partition, each chart on one of the machines. So that's pretty cool. Why is it good beyond the fact that we can like store more data? Well, it's easy, for example, to do something like a primary key lookup. Okay, so we have like this 1 billion events, but right now I won't only care about event number 100 million. So I want to read the content of this event. I want to see what country it's in. So that's pretty easy because I know that it's in the first table, like in the first chart. And I know if I know where the first chart is, I can directly go to that machine. So I can go to that machine and just query that machine directly, only like 1/10 of the data set, or like if I have more machines, even smaller part, and like do a single node operation only on that part of the data set. And then another thing that we can do is we can do machine level parallelism. So if we wanted to do something simple like select count star from events, like we want to count all the events on all the machines, we can launch this query on all the machines in parallel. So we can benefit from having 10 or 100 machines execute parts of this query for us. Okay, but then with great power comes great responsibility, Spider-Man and all that, which in our case means roughly you can't expect 100 machines to just stay up. You need to be careful about keeping the machines up. I'm going to give you a quote as an example. I'm not going to like throw statistics on mean time between failures, but like this is a quote from Jeff Dean, who is one of the more famous engineers at Google, currently a lead of Google AI. So in each cluster's first year, when Google creates a new data center, within the first year, about 1,000 individual machine failures will occur. Thousands of hard drives will fail. One power distribution unit will fail, bringing down 500 to 1,000 machines for about 6 hours. So you have 100 machines, maybe like they just all done at that point. And also like another part that they wanna focus on is 20 racks will fail, causing 40 to 80 machines to vanish from the network. Like the network is another thing that's constantly failing in addition to machines. So like this is the Google scale, but you don't really need to be Google to hit this. At the company that I work at right now, we're like very far from the scale of a whole data center, but we still hit individual instance failures like maybe every once a week or once 2 weeks. We've heard from Amazon that this is because we're using one of the new instance types, so they're not stable yet. But like the fact is, we are using a production AWS instance and it's like failing constantly. So how do we stay responsible when faced with so much machine failures and like all concepts of failing? Well, what we can do is like the standard approach is to use a replication. So the idea with replication is now instead of just keeping each chart on one machine, we put each chart on 2 machines. Like we copy each chart twice or 3 times or more, it's depending on how reliable we want to be. So now, if machine 1 fails, then we also have a copy of the chart 2 on the next worker as well. So we can recover that data from there. So why is that cool? In addition to like machines failing completely, we can also do like failover at query time. So if you're looking for the first event, like the first millionth event, which we know is on the first machine, but then while we're doing that, the machine dies, and it doesn't give us a response, we can just directly query the other machine that has this shard. Okay, this is all pretty standard. The next thing is like another benefit of replication that's like a bit more unpopular is something called speculative execution. And the concept behind that is that any individual machine can be very slow at a given point in time. For example, maybe right now I have queries that are only hitting one machine instead of all 100 in my cluster. Or maybe there's like garbage collection and background system processes running on that machine. Or like all kinds of stuff can make a machine slow. So the idea here is that if we want to query for event number 100 million, or just 100 or whatever, we can, instead of only sending a request to worker number 1, we can also send a request to worker number 10. Because we know that both machines have the same data, like that part of data at least is from both machines, the shark events underscore 1. We can send the request to both machines, and then whichever machine replies first, we go with that. So like that's used in some data computation systems like Spark and Hadoop, for example. Google have also mentioned using that internally in a bunch of places. Cool. So that's the fundamental concept. The cool thing is that it's a pretty general pattern. Like these are the basics, but like a lot of things are built on them. Like for example, Kafka, which is a distributed lock system. Is like you have a lot of topics where you can send messages. Each topic is sharded into partitions. And each partition, like this is the partitioning or sharding, and each partition is replicated on multiple machines for resistance. HDFS, the Hadoop distributed file system, and also GFS, which was Google's original distributed file system. They store large blobs, like large files. For example, you have a 10 terabyte file and you want to store it somewhere. Those are also split into chunks or blocks of, like, for example, 100 megabytes or like 128. And each block is replicated on multiple machines for failures and for more efficient management and all that. And this is also the case with more production-ready or like commercial systems like Google's Spanner, Amazon's DynamoDB, which are like classic examples of distributed systems. Cool. But then the thing is that, as we mentioned, the failures, like they're constant failures, and also the network is like can be one of the fundamental concepts in building distributed systems is that the network can be very, very, very slow and unreliable. So like at any single point we can have just random packets from the network dropping, or we can have a network partition, which means that like one part of the data center can talk to each other, and the other part of the data center can talk to each other, but they can't talk to each other. So what are the kinds of things that we need to think about? What are the trade-offs that we possibly need to make? We'll start with something called the CAP theorem. It's like a classic result in distributed systems, which says that a system cannot be both consistent and available in the presence of network partitions. So I've bolded all these words because they have like very, very precise theoretical definitions in the proof of the theorem. And they also, like the proof applies in like very specific, well-defined theoretical models. So like I'm not going to give definitions here because like most people are not really big fans of theoretical definitions. But like keeping that in mind is important for like understanding how new systems deal with those kinds of failures and how some new systems supposedly did the CAP theorem, which has been acclaimed lately. Okay, so what is the CAP theorem? What does it mean that you can be consistent and available in the presence of network partitions? So let's say you have like a very simple setup. We have two machines, and both of them are storing the same number. They're storing the integer x, and initially it has the value 0. And then we send an operation which ends up at the first worker, which says write the value 5 to x, set x equal to 5. And worker 1 applies that operation immediately. But then the network partitions, and it can't get to, the other part also says worker 1. I say that now, okay? The other worker 1, the worker 1 on the right, doesn't get the message, so it keeps having a value of x equals 0 because the network is partitioned. And so now when we get read operation. Like if we, at this moment, we get a read operation which ends up at the other worker, like imagine it's called worker 2. But if we get an operation that says, I want to read the value of x, we have two options here. We can be consistent, which means return the last, like informally it means return the last value that was written within the whole system. In our case, that's 5. And because we don't know that this is the value, we need to detect that and not like return an error, give up and say, okay, I can't service this request because there's a network partition right now. That's a consistent option. And then there's the available option. The available option says, informally again, if I'm up and alive, like as a machine, then I need to send a response to this query. So what am I gonna do? I'm gonna say, okay, x equals 0, which is gonna be wrong, like from the perspective of the whole system, but maybe it's still valuable to be up. Okay, that's like the basics. And this is like kind of a simple example, but it also applies to much larger systems. But the thing is that there's like a lot of nuances. Like this is the simple claim. In the presence of partitions, you can be both consistent and available. There are a lot of nuances that matter in terms of how we build or choose systems that this theorem applies to. So one of the first nuances that you hit once you start thinking about it or like reading about it is notice how I code this with 2 letters. Like consistent is CP, which means that in the presence of partitions, the system is consistent. And AP means in the presence of partitions, the system is available. So basically, it's like from the CAP theorem, from consistent, available, and partition tolerant, we can only choose 2. So we choose either AP or CP. And so one of the classic jokes is consistent and available systems, also famously known as I don't know how networks work. Because if you say that your distributed system is consistent and available, that means that you're implying that there are no network partitions, which is like currently reportedly impossible from most of the claims on non-distributed systems and networks. And then the other, like the strictly theoretical question is, if there is a partition, what does your system do? Because like as we saw, it's theoretically impossible. You can't know the value of x on the other machine. So yeah, like I said, there are a bunch of new recent systems that claim to be CA, so consistent and available. We're possibly going to cover how that could happen while still not violating the CAP theorem. Cool. Some more nuances, like I mentioned, consistency and availability are defined in like fairly strict terms. So once you start building or using such a system, like realistically, most people are not going to build a distributed database system, but a lot of us might need to use one. So you need to make the choice: do I need to use a consistent system or an available system? But then you also need to get into the nuances and think about, okay, do I need consistency in the way that it's defined in CAP, and do I need availability in the way it's defined in CAP? So one famous example is with Amazon's database called Dynamo. This is one of the first like more famous papers on distributed systems in the real world that made this trade-off. So the interesting is that for business reasons, they decided that they don't really need to be consistent. And what does that mean in their case? I've underlined a part of the sentence here, but the shopping cart service must allow customers to add and remove items from their shopping cart, even amidst network and server failures. That basically means that for Amazon's business, it's very important that whatever ends up in your cart stays there, whatever happens to your servers and your data centers at that point. And one detail that's like even more interesting for me is that they decided that like if there's a partition and they become inconsistent, so that like all the requests can still arrive. Like after the partition is done, you need to somehow reconciliate, like decide what should actually be in the system. Like what's actually in a user's cart if they added things and removed things during the network partition. So they made a decision that when merging these things, they merge add to cart operations, but they might ignore remove from cart operations. So what does that mean? It means that if you have the same user doing this sequence of operations, like open one session, add item like some book or like some router, to your cart. I want to buy item X. And then like 5 minutes later, you open your browser again, but you hit a different Amazon server. And that different server is partitioned from the first server, so it doesn't know that you added X. And you say, oh, okay, I wanna remove X from my cart, and I wanna add Y. I found a better router, so I don't want to use buy the previous one. I'm gonna buy the second one. So Amazon says, okay, I'm gonna add Y to your cart. And then when the partition is over, you end up with a card that says, oh, he's gonna buy X and Y. Because Amazon doesn't want to lose additions to your cart, because those bring in business, but they are willing to lose removals. So like Amazon are fine with you having to remove a router from your cart because you added it by mistake, but they're not fine with you having to add it again. They don't want to lose business by this. So then another nuance is, okay, so you decide, okay, during network partitions, I want to be available. But most of the time, there's no network partition. Like network partitions are a failure mode that needs to be handled generally, but like realistically, they don't happen most of the time. So what about during normal operations? And one interesting thing is that lots of databases sacrifice consistency even without partitions. Classic examples of this are MongoDB, Cassandra, Amazon's Dynamo that we just discussed. Even single node systems like PostgreSQL can sacrifice consistency in the default isolation level if you don't explicitly do something to change that. So why do databases like this sacrifice consistency when there's no partition? So like the network is all working fine, but there's still no consistency, still no transactions, still no asset in the classic database terminology. Well, it turns out that transactions are like very, very hard on your latency as well. So as soon as you introduce transactions, all the operations in your network database possibly start being very slow. So like transactions in the distributed database can be very slow. So a professor from, I don't remember where, but his name is Daniel Abadi. He's like very famous in the database world. Introduced a theorem called Paselk, which is not as catchy as CAP. So I'm pretty sure that's like part of the reason he didn't catch on as much. But it says if there's a partition, you need to choose between availability and consistency, which is the part that we saw so far. But then if there's no partition, else, you need to choose between latency and consistency. So if you choose to be consistent, even when there's no network partitions, all of your operations might start being very slow, and you can incur a lot of latency on your database. Cool. Another problem that, or trade-off that needs to be made is when you need to do Crossshark operations, like joins, group bys, distincts, or a trickier thing is Crossshark transactions. So just as a quick example here, if you want to do a select count of distinct IDs from this table, I'm not going to go into this in detail, but if you think through this, like how this query can be executed, you're going to realize that because all the IDs are distinct, here we can do something simple. Like we can say, oh, there's like 100 million distinct IDs on each machine because we partitioned by ID. But if we had partitioned by something else, we would need to accumulate all the IDs on the central machine and just do some operation on them, like union all the sets, like have a single machine be doing a ton of operations, being a single point of failure in our operations. So like that's also another trade-off that needs to be considered when you're introducing sharding and partitioning into a system. This all sounds pretty theoretical, but an interesting thing is that it's actually not. Like I said, most of us are probably not going to be building distributed systems, but a lot of us are going to be using them in some form or another. So I'm going to give two examples. One is like very specific and concrete, and the other is like more of a meta example. But like the specific example is that AWS S3. How many of you have used S3? Okay. Yeah, so S3 is eventually consistent. So when you insert an object, it doesn't immediately become known to like other participants in the system. Like there's one very specific case in which it does, but like in all others, it doesn't. So you can do something like write a new object. Like this is from the docs directly, but I've highlighted some parts. But a process can write a new object to Amazon S3 and immediately list the keys within this bucket. like this is all the same process. Like we don't even have a distributed, like we don't have parallelism within our system. We're just using S3 from a single process. So we can list the keys in the bucket, and until the change is fully propagated, the object might not appear in the list. And then the other is a process can delete an existing object and immediately try to read it. And Amazon S3 might return the deleted data. So that means that the sequential execution of logic that you're used to from single-threaded programs, like I'm going to delete this object and I'm going to try to read it, and it's all going to fail. This is wrong if you're using S3. Or if I write this new object and then I list the directory in which it is, it's like a bucket in Amazon S3 terms, but it's like a directory. But I can do that, and the object may not be there. Like it might be there, but it may not be there as well. So like part of the concerning bit is that it's called eventual consistency, which means that if you don't write, like if you stop changing the object, eventually at some point in the future, all readers will converge on the same value. But there's like absolutely no strict guarantees on when this will happen. So in theory, it could be seconds, but in practice, it could be hours. Or I'm going to say in practice it can be multiple minutes because I'm pretty sure I've seen that happen. In theory, it can be hours because Amazon doesn't give you any guarantees. And the meta example is something called Jepsen. How many of you have heard about Jepsen? Okay, so Jepsen is a very cool, the part that's most familiar to me is like a very cool series of blog posts. But it's like a system that's used for testing distributed databases. A guy called Kyle Kingsbury called it, and he's like experimenting with different distributed and non-distributed databases and testing if they do what they say they do. So, like for example, if a database says it's consistent, Jepsen is there's a system that's part of Jepsen that can run multiple tests on it and see if it's actually consistent. And they're like, if you have time, I would advise you to go there, and like if that's an interesting topic to you, they're like very popular databases that are tested there. I'm going to give just one specific example. Kafka. So just like how many of you have used Kafka or are familiar with it? Okay. So Kafka is like a distributed log, like I mentioned a bit earlier. But the idea is that you just send messages to it and it writes them, and it writes them in a durable way, in a very performant way. Supposedly they're like durable. But here are the results from the Jepsen tests of Kafka. Like there's like one caveat, which is that this test is from maybe 6 years ago. So things changed since then, possibly. But what happened when they were testing it is that Kafka acknowledged, so like basically what happened is that they started a Kafka cluster and they started sending messages, and then they partitioned the network. And like Kafka had to make this choice. Do I want to be available or consistent? So Kafka made the choice that, like supposedly Kafka, according to the docs, makes the choice to be consistent and available, which like we saw is usually a fraud. But what happened is that between 98 and 100% the flights were acknowledged. So Kafka said, "Oh, that's okay. I wrote almost everything that you sent me to persistent storage." And then after the partition recovered, so like they connected the network back again, there were 520 acknowledged writes that were lost. So you say to Kafka, "Okay, I want to write this message," and Kafka says, "Oh yeah, cool, it's done. I wrote it." And then like 2 hours later, your network recovers, gets in a better state, and Kafka realizes, "Oh, these messages were not actually written in my internal definition, so I'm gonna get rid of them." And you lose like 50% of the messages that you send in a failure scenario. So, like I said, there are a lot of different tests for this. There's a test for Redis, which is also pretty fun. If you're interested in this subject, I advise you to go ahead and read this. Okay, extra credit. We have a few different options that we're not going to be able to cover. Okay, I'm going to talk about erasure codes. How many of you are familiar with erasure codes or Pete Solomon or something like this? I see one person maybe. Okay, the idea with erasure codes is that you can use some kinds of like linear algebra and like more complicated things to encode some relationships in your data, and you can do that with the idea that you can make the data more reliable. So, for example, you can do stuff that's like for every read Solomon codes allow you to add 4 bits to every 10 bits, for example, in a way that you can actually tolerate the partition of like half the original data, tolerate the loss of half the original data. So like that can save a lot of storage space in comparison to the replication, which was just like, I'm going to copy all the shards over. The idea is I'm going to use some complicated math, or not some complicated, but I'm going to use this math in order to replicate the data in a way that's more efficient. And okay, a couple of tidbits, like how do you beat the CAP theorem? Like there are a few systems lately. One is Apple's Foundation DB, one is Google's Spanner DB that claim to beat the CAP theorem, which, like you said, is like kind of hard because like how do you know the different values if there's a partition? So one interesting thing is that they usually beat it by slightly changing the definitions and slightly changing the rules. Like for example, Apple's Foundation DB says something like on the docs, something like this is like what we do is high availability as usually understood, but it's not availability in the CAP sense, which is like more accurate and slightly different. But in the end, like in strict CAP terms, it's still a consistent and partition tolerant system. And Google Spanner, they basically build a system that's like so stable, like the network is so stable that they basically assume that it never fails. In fact, it turns out that it does fail sometimes. And when it does fail, Spanner is going to choose to be consistent instead of available. So it's also a CP system in CAP terminology. That's like just a quote from one of the guys that actually created the CAP theorem, which just says, the short answer is no technically, as in is Spanner a consistent available system, but yes, in effect, and its users can and do assume CA. Okay, yeah, that's about it.
Awesome. I think we have time for questions, so raise your hands if you want to ask something. Any questions? Oh, there is a question. You ready?
So, hi, thanks for the talk. It was very interesting. You spoke a lot about scaling data in order to be able to store more data. Do we need to scale data in different locations? What can you tell us about that?
Like scaling between data centers?
Yeah, there's in different locations. Like, how do we decide what data to store in different locations?
Sorry, can you elaborate? I'm not sure what exactly the question is.
I mean, do we need to have different databases that are stored in like different parts of the world?
Oh, got it. I mean, yes, some databases do that. That's what's usually called data center replication. Like for example, Amazon and Google definitely do this for some of their more important services. Maybe for most. Like the idea is that there can be like there are a lot of energy outages right now in California. So there could be like a data center outage, something that affects your whole data center. So in that case, you need to fall back to a different data center. But that's like in the case that you're Google or Amazon. For most like smaller companies, it usually adds another layer of complexity to what we talked about in the last 40 minutes, or 30 minutes. And like if you can, basically there might be ways to make the problem simpler. Like for example, in the company that I work at, one of the core components is data collection. So we collect data from various sources. So that's I think the only part of our system that's data across data center. So if a single data center fails, we're still going to keep collecting data because that's very, very important to us. Like not losing data is very important. But if we lose the data center where our UI backend is hosted, for example, people are not going to be able to access the application. I don't know if that answers your question.
Yeah, I guess.
Okay.
Can I ask something that adds a little detail on that?
Okay.
Does it make sense to scale data given the business case? I mean, if we have software that scales around the whole world and maybe some data is important to different parts of the world, does it make sense to scale it in a way that we optimize storage?
Yeah, it could. Like, for example, a possible thing that you can do is in order to minimize the latency that it takes to get to your data. For example, I think Facebook does this, probably other places as well, definitely. But like one thing that Facebook sometimes does is it keeps copies of your data in a data center that's closer to you. Like, for example, if I'm accessing Facebook right now, I'm probably not going to hit the data center that's in the Western USA, but I'm going to hit like one that's in Europe because it's just going to take like a smaller network latency to get there. Just because at some point you're fighting with, like you just need to get this data from one end of the world to the other if it's at the other end of the world. So yeah, you could make sharding that's like focused on different parts of your user base.
Okay, thank you.
Here. Any other questions? Oh, there's one. Please stand up asking the question.
What are your thoughts about CockroachDB? Do you think it can you use it like Google Spanner?
So what's the question?
What are your thoughts on CockroachDB?
CockroachDB. Yeah, from what I've read, CockroachDB is based on the Google Spanner paper, but it doesn't have two important components. One is the network in like Google's physical network in the data centers. So like this paper that I quoted by Eric Brewer, which is literally the person that created the CAP theorem. So like he works at Google now, so probably not completely objectively. But like the paper goes at length through the fact that a very important part of making Spanner close to CA is the network. Like the network is extremely reliable. They have like out of each data center, they have like 3 network connections to the outside world. Within the data center, they also have like a super reliable network. And they also have like atomic and GPS clocks and all that. From what I've read, CockroachDB doesn't have all this. So I don't, as far as I understand, they can't claim to be consistent and available just because network partitions are not in their control, because they're like the software. It might be like, I don't know if they have a hosted solution. But in general, if you deploy CockroachDB on your own data center or in AWS or whatever, which has network partitions, you're not going to be able to fight with that. But I think it is like a consistent end partition of tolerant database.
Right. We have time for one last question. All right.
Good shot.
So, can you tell me the question and I'll live translate?
You mentioned that not losing data is very important, and I imagine the inverse is also a problem, where you receive data more than once.
There's microphone, sorry.
Did you hear my question, or should I repeat?
I heard parts of it, but
Repeat it for the stream, please.
Okay. So you spoke about that it's important to you not to lose data, and I imagine the inverse is also a problem where you receive data more than once. So I was wondering, is exactly once delivery possible or a problem?
I mean, based on all the theory, exactly once is not possible. Like there have been claims lately, like Kafka claims that they have exactly once. It's like a very limited way of defining exactly once because they have exactly once within Kafka. So like the main problem with exactly once is that once you have side effects, you can guarantee that these side effects only happen once. So for example, if you're trying to send an email in response to a message that you received once, you can be 100% certain that you did or didn't send the email. So if you receive the message again, what are you gonna do? Or like, I guess the more accurate way to describe it is, if you fail to receive acknowledgement of the sending of the email, what do? Do you give up or do you retry? So like if you give up, maybe the email never did get sent. Like you didn't get an acknowledgement because the email wasn't sent. But if you do retry, maybe the email was already sent. And you just didn't get a reply because your network was unstable at that point. So as soon as you have externally visible side effects that go like outside of your isolated system, I think that the consensus is that exactly once is not possible. As long as you're within your system, exactly once is possible in some definitions. Like exactly once usually means that I have idempotent messages so I can retry them multiple times. That's what usually people mean when they say they have exactly once. I think that's what Kafka means when they say they have exactly once. But in general, with side effects, it's like impossible, I would say.
All right. So
thanks everyone.
Again, big round of applause for Ivan.